Alright, section 1.10, data and modeling. Um, this is kind of a substantial amount of information, but it all makes sense. It's all pretty simple. It's just a few different formulas we're going to go through here. And we're actually going to be doing a group project this week based on part of this information. Alrighty. So here's our to-do list. Least squares regression, direct variation to the nth power, inverse variation, and joint variation. Alright? So, first thing, and this is what I think we're going to be doing our group project on, is called least squares regression. So if we're given a set of data, not just an equation that represents data, but just data. So this is the way things work in the real world, right? This, for instance, is Broadway ticket sales in millions. We see in 1995 there was 406 million ticket sales. 1996 there was 436 million ticket sales, and so on. What we want to do here is use our calculator to find a equation that will model this information. Okay, and so we're going to go through and do this together. What we need to do is plot these points, and then the calculator will figure out a line, the best fit line will go through those points, and that will be our model. So what we need to do here is, be nice with that. Okay, we're going to go to Stat and Edit. Okay, so we click on Stat, we go to the first thing, which is Edit. And this is L1, which is going to be our year, which are our X values. I put them in. You're basically just going to go down, you can type. So you hit 5, it'll work. And you go down the list. I put in 5 for 1995, 6 for 1996, and so on. So 2001 will be represented as 11. Our L2 list, our second set of data, is going to be our sales in millions. Okay? Then what we need to do is go to second stat plot and make sure that it's on. We hit enter, we turn it on, we hit enter. We're going to want to go down and use L1 for X list, L2 for Y list, and also from these 6 choices we want to use the first choice. It's like a plot, stat plot. Okay? Alright, and to then graph these, we're going to go to second zoom, which is not second zoom, we're going right to zoom, and it's going to be zoom stat number 9. And then we go ahead and enter, it's going to plot these points. And what I did, though, this is very important, the window. Alright, I actually put 0 because, we're going to say we're starting 1990. We don't really do that, we're going to go back. The max I put in 11 because it only goes up to 2001. That's 11. I put 1 for the scale. Our min I put in 400 because our highest value or lowest value is 406, and as a max I put in 700. And for the scale I just put 50 because that makes sense. I mean, you want to make it a value where we're going to be able to visualize this. If we put 1, that's going to be 300 bars on the y-axis. It's going to be a little bit confusing. So then, yeah, we go to stat, zoom, go to zoom stat, hit enter. Alright? Now you see that this isn't a straight line necessarily. They're pretty close to a straight line, but it kind of goes up and down a little bit there. So what we want the calculator to do is find our best fit line. And what information do we need for a line? We need the y-intercept, so we want to know where it's going to start, and we want to know the slope. Okay, and how do we do that? We click on stat, we go to calculate, and we're going to go to linear regression, number 4. Alright, hit enter, enter again, it's going to calculate it. So it says y equals ax plus b, that's kind of like our slope-intercept form. You see it's y equals mx plus b, but it gives us a, that's basically going to be our slope, and it gives us b, the y-intercept. Alright, so I'm going to go ahead and write that down. We'll do 42.964 for A, and B equals 192.857. 192.857. 0.857. So then we know our line is going to be 42.964x plus 192. And so basically what this number right here is, the 192, that's our y-intercept, which is at 0. So they're pretty much predicting that in 1990 there was 192 sales, 0.856. Makes sense, right? Because this is at 5 in 1995, and this is when x is 0, which is the y-intercept, which must be 1990, 192. So then we can go right back and we can plug this in too. We can go to y, we can say 42.964x plus 100 plus 192.857. If we graph that, you'll see, look at that, pretty close. So our calculator tells us this is the best fitting line to our data. Alright? So that process I just went through is important for you guys to know. Go back and check it out if you need to. You need to enter the lists of data, and then you need to graph it, and then we go to stat, and we calculate the linear regression, and it will give us the information we need. What we're going to be doing for this group project is finding data in the real world and trying to we'll be able to predict sales. So based on this graph, alright, so if we want to figure out or estimate what it's going to be in 2005, what are we going to do? We're going to plug in basically 15 for x. Right? So we're going to get 42.964 times 15 plus 192.857, and we're going to see that that is 42.9 42.964 times 15 plus 192.857. They predict there will be 837 basically sales in millions in 2005. Alright? Makes sense. Kind of cool. You're able to take information from the real world, match a line to it, the best fitting line, the least squares regression line, and then you can estimate points from the future. Okay, the next thing we're talking about here is direct variation. So what this is simply something, y, will be directly related to a constant, k, times one variable. That's direct variation. So for instance, Scotty, our boy Scotty, makes $5 an hour working at Chuck E. Cheese. So y equals 5 times x. That's basically just a line, right? A line with a y-intercept of 0. So as x increases, y is going to increase. Okay. Another example, and every week you work out, you lose 3 pounds. Well, this is negative 3 because we're losing 3 pounds. So, well, in 5 weeks you're going to lose 15 pounds. So, makes sense. In 3 hours, Scotty will make $15. Okay, he'll be loaded. You can also have direct variation to the nth power. So before we had y equals just k times x, now we can have k times x to a power. And an example of that we all know is the area of a circle is equal to pi r squared. So your variable is that r, and it's to the second power. Your k is that pi. Okay, and you see that this makes it increase faster. So when the radius is 1, the area is pi. When the radius is 2, the area is 4 pi. When the radius is 3, the area is 9 pi. So on. So you're going to have an exponential graph, as opposed to the first one, which is just a line. Alright, next thing we're going to see is inverse variation. Alright, this is when you have a constant k divided by your variable. And this is obviously, as x increases, y is going to decrease. And here's an example. We have 10 candy bars, and we're going to split them split them among a group of children. Well, if we only have one person, that one person's going to get 10 candy bars. If we have two people, they're each going to get 5 candy bars. 3, they're going to get 3.33, obviously, and you're going to end up having a graph that looks like this for inverse variation. Okay, as x increases, y decreases. Right. Here's another example. A biker traveling at 8 miles per hour can cover 8 miles in 1 hour. So basically we're saying if he goes 8 miles per hour, it's only going to take him 1 hour. Well, that's that point right here. If he's only going 1 mile per hour, it's going to take him 8 hours. So as he increases his speed, the time will take less. That makes sense. I mean, the faster you're going, the faster you get there. That's basically what that's saying. Alright. The last last piece we're going to talk about here is joint variation. So now we have two constants to a power. Alright. So now before we were saying, for area of a circle, it's just pi r squared. So that's your one variable. Well, now we have two variables. An example of that is a triangle. We have base to the first power, height to the first power, so that's your n and m. And both the base and the height affect the area, alright? You increase the base, you're going to increase the area. But also, if you increase the height, you're going to increase the area. This area is directly related to both the base and the height. Alright? It's another example. Volume of a cylinder. The volume of the cylinder, the formula that we all know is pi r squared times the height. Well, here's your x to the n, and here's your y to the m. So we had, just going to go back, we had z equals constant times x to a power times y to a power. Well, your constant here is, your z is the volume, your constant is pi, your r squared, or your x to an n is r squared, and your y to an m is just the height. Alright? So basically all these different things are different ways that the values, so z or x or y, are related to each other, okay? I'm just going to go through it real fast and just recap, okay? So we have direct variation, where it's simply one variable and the other variable is directly related to that increasing or decreasing. Y is directly related to x, with a constant as well affecting it. Okay? Here, it's direct variation to the nth power, so it's only one variable, the x, but now it's to a power, and then we saw pi r squared for that. Inverse variation is, as it increases, it's going to decrease. As x increases, y is going to decrease, as opposed to the first two, as x increased, y is going to increase as well. Okay? And then finally, joint variation, where it's directly related to two different variables. Two different things are affecting the final thing, the final value. Okay? Sounds good. Alright, question time. There's only two. This is the kind of stuff we're going to be spending a decent amount of time in class, so I only have two questions, and they're not very difficult. But hopefully you pay attention, because we have that group project, so see you in class.